Welcome to Opportunity Crudes Management Seminar Series, an informative look at crude processing challenges. Disclaimers. The purpose of the OCMS series is to provide refiners with the latest information in processing opportunity or price-advantaged crudes, such as heavy sour oil, oil sand bitumen, light tight oil, and highly acidic crudes so that they can make better decisions in light of a volatile oil market. In our third video, Do You Have the Right Stuff? Crude Cuts, Part 1 Crude Selection, we discussed important selection criteria for refiners when buying crudes. In a volatile oil market where refiners often buy and blend inexpensive crudes, determining crude compatibility is very important. If incompatible crudes are blended, numerous problems arise that can result in financial losses, eliminating the benefits of sourcing cheaper crudes. In this video, we will focus on many topics about crude incompatibility, including recent news events concerning crude compatibility and the causes and effects of incompatibility. We will also focus on asphaltene instability, which is a major consequence of blending incompatible crudes, types of crude incompatibility, methods to determine the compatibility of crudes, and commercial services to prevent crude incompatibility will also be discussed. Navigate oil market uncertainty and supply disruption in refining at the 6th Opportunity Crudes Conference in Houston, Texas in the U.S. from October 22 to the 24th, 2018. The theme of the conference is Crude Disruptors, Accelerating Changes in Global Refining. Higher oil output and refining price advantage. Domestic light tight oil has benefited international oil majors and U.S. independent refiners in the first quarter, respectively, according to just released earning results. Unfortunately, the good news will end soon as the oil market is going to enter an uncertain time since the price rout in mid-2014. A dark cloud is forming as driven by two formidable forces, geopolitical risks and changing supply-demand fundamentals. Change is not new in the refining world, but disruption of crude sources could significantly upset overall refinery operations in terms of crude management, processing, and product quality and volume. Our attendees will learn from conference speakers and network with colleagues on how refiners can navigate present market uncertainty and crude supply disruption by devising better business strategies, finding ways to increase operational flexibility, and adopting new technologies to turn challenges into opportunities. As in our previous meetings, this conference is expected to be highly productive and rewarding because of excellent speakers, timely theme, well-organized agenda, and stimulating atmosphere to encourage exchange of ideas. 5 topical sessions in 2.5 days include: Session 1, Global Oil Market Outlooks, Geopolitics, U.S. Pro-Export Policy, OPEC Strategies, Peak Demand. Session 2, Challenges and Opportunities in Oil Trading, Exports, Imports and Infrastructure Logistics. Session 3, Crude Contaminants, Incompatibility, Blending Strategies Amid Changing Feedstocks. Session 4, Flexibility of Light Tight Oil Processing and Bottoms Upgrading to Make Products in Demand. Session 5, Big Data Analytics and Emerging Adoption of Internet of Things in Crude Selection, Management, and Refining. In this celebrated biennial meeting, you will meet colleagues from many companies around the world. The Opportunity Crudes meeting from October 22 to the morning of October 24 is coordinated with Crude Oil Quality Association's fall meeting, which will be held on October 24 and October 25 to benefit from synergy in serving our upstream, midstream, and downstream colleagues. To save up to $300 before June 1, register today by visiting opportunitycrudes.com/Houston 2018. Here is a preliminary agenda for the 6th Opportunity Crudes Conference. Declining crude prices have been encouraging refiners to make more spot purchases that save feedstock cost. A practice becoming more common is the purchase of look-alike crudes, which are blends of different crudes to create a grade with properties acceptable for processing. Also, there have been a number of global events driving refiners to buy new crudes for the first time. However, Trying new grades poses many risks to the refinery as the properties of these new purchases may not be yet known and may be incompatible with other crudes if blended. The issues created by incompatible crudes often eliminate the benefits of buying cheaper grades and blends. To cut costs, refiners often rely on so-called look-alike grades made from a blend as replacement for certain grades. In the United States, refiners have been able to replace valuable crudes with look-alike grades made from certain blend recipes. These recipes include Bakken and West Canadian Select to make a blend similar to Alaskan North Slope, Mars and Eagle Ford for light Louisiana Sweet, and Canada's Cold Lake and North Dakota Light for West Texas Sour. However, these blends can be far from a perfect match. For example, the 50-50 blend of Canada's Cold Lake and North Dakota Light has shown to have lower distillate and higher resid compared to authentic West Texas Sour. Multiple refiners all over the world have been aware of crude compatibility issues when buying new crudes for the first time. For example, as a result of new U.S. imports due to the lifting of the export ban, a Japanese refiner conducted extensive laboratory analyses of U.S. crude to determine the compatibility of these grades with other crudes. Back in September 2015, a 995,000-barrel cargo of 23.5-degree API Basra heavy crude from Iraq was on its way to Galveston, Texas. Market sources state that a local U.S. refiner was using this initial cargo for an initial test run to see if the grade is compatible with its existing U.S. Gulf Coast refining capacity. An energy company is planning to open a heated 100,000-barrel tank at its crude-by-rail terminal in Beaumont, Texas that would blend undiluted heavy Canadian crude with super light condensate or tight oil. As part of the new endeavor, the company is taking steps to ensure that the crude headed to the refinery is, quote, compatible and consistent. Crude incompatibility that leads to fouling problems is often caused by changing the ratio of four crude oil components that are defined by polarity and solubility. These components are saturates or paraffins, aromatics, resins, and asphaltenes. The acronym SARA is often used to refer to the four components. There are three types of crude compatibility issues that refiners must be aware of. These are self-incompatible crudes, incompatible crude blends, and nearly incompatible crudes. In this seminar, we will discuss the unique characteristics of each of these compatibility issues, models to determine crude compatibility and to predict fouling, along with commercial options including software and analyzers will also be discussed. IRV of Soluble Solutions has created the colloidal dispersion solution model, which shows how asphaltenes would normally behave in stable crudes. First, the asphaltenes, which are considered the solute, are dispersed by resins, the dispersant. Later, the complex is dissolved by small ring aromatics, the solvent, then later by saturates or paraffins, both considered to be non-solvents. The image on the right shows WE's model. Self-incompatible crudes are those that are prone to asphaltene destabilization and fouling even when not blended with other crudes. Such crudes are more likely to cause fouling and processing problems than compatible crudes. More than 30 such crudes have been identified, including Mexican Isthmus grade, even though it has been recommended that refiners generally avoid buying self-incompatible crudes. The frequency of self-incompatibility observed for West Texas Intermediate is increasing due to accidental and intentional contamination. Intentional contamination occurs when tight oils are blended with West Texas Intermediate along with Canadian heavies to match the gravity and density specifications of West Texas Intermediate but result in the precipitation of asphaltenes. Since 2011, it has been found that 75% of West Texas Intermediate to be incompatible, compared to no incompatible samples found before 2011. To avoid self-incompatibility, it has been recommended that increased testing be done for compatibility as well as transport of crudes that are compatible with both light oils and heavy oils in between shipments of the latter two. Incompatible crudes are those that are stable individually but unstable when blended. When incompatible crudes are blended, A change in the ratio of the sera molecules or an increase in the concentration of saturates such as paraffins may occur. Both of these events may lead to asphaltene destabilization. In general, mixing asphaltenic crudes with crudes that are more paraffinic, such as light tight oils, causes the asphaltenes to become destabilized. Crudes being combined in the wrong order is a reason for crude incompatibility. Other reasons for incompatible crude blends include incompatibility over some range of composition, and, for certain blends, high temperatures. Incompatible crude blends cause asphaltene and paraffin immiscibility, leading to asphaltene precipitation. This has numerous deleterious effects in the refinery, which include lowering of capacity in crude tanks, emulsion formation in the desalter, and fouling and coking in preheat exchangers, distillation unit furnace tubes, and catalyst beds. In order to avoid these problems when blending tight oils and heavy crudes, refiners should blend tight oils with heavy crudes with an API gravity of 13 to 16 degrees to yield a blend with an API gravity of 21 to 23 degrees. According to the oil compatibility model, which is one option for determining compatibility, nearly incompatible crudes have a solubility blending number to insolubility number ratio in the range of 1.0 to 1.3. Nearly incompatible crudes are likely to cause moderate fouling and contribute to rag layers or emulsion layers in the desalter, because nearly incompatible oils form smaller asphaltene particles than those formed by incompatible crudes. Nearly incompatible oils cause more stable water in oil emulsions. Thus, the smaller asphaltenes are able to more tightly surround water drops. The blending of incompatible crudes will often change the ratio of the sera molecules. This may ultimately result in asphaltene instability. For example, the mixing of more asphaltenic crudes with more paraffinic crudes such as light tight oils. Research has shown that the total quantity of asphaltenes also has a direct effect on the severity of asphaltene fouling. As a result of crude incompatibility, asphaltene instability may occur. Asphaltene instability has been attributed to numerous issues in the refinery, including decreased energy efficiency, increased carbon dioxide emissions, a higher frequency where heat exchangers need to be cleaned, and increased crude throughput. In order to prevent these problems, it is important to know the chemistry and structure of asphaltenes. The asphaltene fraction is currently defined as the oil fraction that is soluble in aromatics but insoluble in paraffins. Typically, the asphaltene fraction is identified using its solubility in toluene and insolubility in N-heptane. However, as more research is done in determining the structure of asphaltenes, this standard may change. The asphaltene composition is influenced by multiple factors, including the choice of solvent, contact time, and solvent-to-oil ratio. The exact structure of asphaltenes, however, is still a subject of debate. Further complicating matters is asphaltene composition being crude-specific. The chart on the screen shows the elemental composition of the asphaltene fractions obtained using N-heptane for 7 different crudes. One can see that the elemental composition varies significantly among these crudes. The ranges for the elements on a weight% basis are: carbon from 78.4 to 87.2, hydrogen from 7.0 to 7.6, oxygen from 0.6 to 4.6, nitrogen from 0.9 to 1.6, and sulfur from 3.5 to 9.8. As mentioned previously, there is still no consensus on the structure of asphaltenes. In fact, there are different models with evidence to support each. The two most prevalent are the paracondensed model and the archipelago model. The paracondensed or island or continental model described asphaltenes as large sheets of polyaromatic molecules with alkyl and alkylphenol chains, while the archipelago model describes the structure as naphthenic and aromatic components linked together with alkyl or thioether bridges. There is spectrometric evidence for the structures of both models in asphaltenes. The paracondensed and archipelago model are both shown on the left. A third model proposed by Soluble Solutions describes asphaltenes as having high molecular weight and being comprised of multiple large polynuclear aromatic segments held by dispersion or van der Waals forces instead of hydrogen bonds. The three proposed models state that changing certain sera molecules will cause aggregation. Because asphaltenes are defined by solubility, there are multiple factors, which include solvent choice, contact time, and solvent-to-oil ratio that may affect which molecules would be found in the asphaltene fraction. To minimize interference from these factors, asphaltene tests should be run for at least 8 hours and a solvent-to-oil ratio of at least 60:1 is used. Using a solvent with a low carbon number may result in a lighter, less polar asphaltene fraction. One study has found that only some fractions of asphaltenes defined by N-heptane solubility are responsible for poor processability. More specifically, the study found that the crude fractions that were insoluble in N-methyl-2-pyrrolidone were the most unstable. Furthermore, temperature is an important variable when testing for asphaltenes, as it was found that increasing temperature decreases the onset time for precipitation. It has been hypothesized that decreasing viscosity is the prevailing factor. Several analytical procedures allow refiners to assess asphaltene instability when mixing crudes. According to representatives at a past American fuel and petrochemical manufacturers Q&A session, even though these tests do have their shortcomings, refiners are more likely to face problems if they do not perform any tests. Most tests involve titrating the crude with a non-solvent either by hand or automated process and detecting flocculation either by human eye or using laser transmittance or near-infrared spectroscopy. Bill Iwood of Crude Monitor offers the Blend Compatibility Calculator to determine the compatibility of blending a crude in a diluent. On the website crudemonitor.ca, you can find the Blending Compatibility Calculator tool. To calculate compatibility between a crude and diluent, just enter the blending solubility numbers and insolubility numbers of the crude and the diluent, the percent in blend of the diluent, and the calculator will determine the compatibility as well as the solubility blending number and insolubility number of the resultant blend. To determine blending compatibility, Dr. Irvie requires the resulting p-value, which is equal to the ratio of solubility blending number to insolubility number, of the blend to be equal or greater than 1.3. This calculator requires a more conservative p-value of greater than 2.0. As such, the optimal percentage of diluent in the blend is calculated as that which gives a p-value of exactly 2.0. Crude Monitor's Blending Compatibility Calculator and Crude Density Calculator are available online for refiners for reference. Disclaimer: these calculators have been provided as a tool, and should be used solely for informational purposes. They are not intended to replace your own calculations, as each situation requires specialized considerations. Crude Quality Incorporated accepts no responsibility for any inconsistencies with the actual chemistry that may arise from the use of these calculators. The Canadian Crude Quality Technical Association, or CCQTA, initiated a project to develop a new manual oil compatibility test method that would be different from the existing manual methods, where the details of which are not publicly available, and make it available to the petroleum industry. In this new method, excess amount of heptane is added to 3 different concentrations of a test oil to precipitate asphaltenes, and subsequently enough toluene is added to dissolve the precipitated asphaltenes so that none is observed under microscope. From this data, a plot of flocculation ratio versus dilution ratio is made. This plot allows determination of all the solubility numbers, including maximum flocculation and peptization power of the oil. The maximum flocculation is equal to the solubility blending number and the peptization power is equal to the insolubility number when toluene and N-heptane are used for both. Here is an example of a plot of flocculation ratio versus dilution ratio for Western Canadian Select made using the Canadian Crude Quality Technical Association's method. From the straight line obtained by plotting flocculation ratio versus dilution ratio, all the solubility numbers including maximum flocculation and peptization power of the oil are determined. The maximum flocculation and peptization power of the oil numbers determined by this method can be used for a number of applications. The peptization power of the oil to maximum flocculation ratio can be used to determine asphaltene's stability and to control the process severity and prevent coke formation in the refining process. The two solubility parameters allow the calculation of the ratios at which the mixtures can be incompatible. Finally, the value of the peptization power of the oil is needed for diluents added to make bitumen suitable for pipeline transport. Most methods to test for compatibility determine solubility by titrating the crude with a non-solvent until asphaltene flocculation occurs. These commercially used tests can either be performed by hand or by automated procedure, and the flocculation is either detected by eye or near-infrared spectroscopy or laser transmittance. As flocculation increases, the light transmittance decreases. Spot tests, such as ASTM D4740 and a modified version of ASTM D4870, can also be used to determine the compatibility of a crude blend according to an ASTM manual called Crude Oils. Their sampling, analysis, and evaluation by Harry Giles and Clifford Mills. Spot tests require that a small sample of the blend be analyzed via paper chromatography. A ring around the spot indicates incompatibility. Additionally, for a crude that does not contain asphaltenes, the solubility number may be determined by blending the crude with a reference oil that does contain asphaltenes and then adding N-heptane until asphaltene precipitation occurs. ASTM D7112 and ASTM D7157 are two automated instrumental test methods that determine compatibility and stability. In order to prevent problems with crude instability, incompatibility, and fouling, refiners have multiple commercial options they can use. These options include commercial analyzers, methods, models, and software to predict crude compatibility, fouling, and stability. There are analytical methods and analyzers available on the market to help refiners determine the stability of crudes as well as potential fouling issues. Here is a non-inclusive list of commercial analytical methods and analyzers to determine crude stability and fouling. Here is our sponsor's experience. The Asphaltene Stability Index Test, or ASIT from Baker Hughes, a GE company, is a tool for determining asphaltene stability of crudes and crude blends. Field as its services technology uses a portable automated titration device using near-infrared laser to detect onset of asphaltene flocculation. The testing can be routinely performed in the refinery. The ASIT plot is the normalized laser power intensity on the y-axis versus the asphaltene stability index, or ASI, on the x-axis. The curve inflection point is the asphaltene flocculation onset and ASI value for the test. In the chart depicted, the black curve represents the base crude for the refinery with a moderately stable ASI value. The blue curve is an opportunity tight oil with no well-defined flock point. Additional information is required to define the ASI value of this type of crude. The red curve is the targeted blend of base crude and opportunity crude, demonstrating a very unstable crude blend that will require problem mitigation. Blend asphaltene stability information can be used to help guide crude selection, blend ratio decisions, and problem mitigation planning to manage risk and maximize refinery profit. Data obtained using the Field as its services technology can be coupled with the BHGE crude compatibility model to further evaluate blend stability for new and proposed blends. There also exist commercial software and simulators that predict fouling in refinery equipment. Here is a non-inclusive list of commercial software and simulators that can predict fouling in various parts of the refinery. There are commercial analytical methods and analyzers to determine crude compatibility. Here is a non-inclusive list of commercial analytical methods and analyzers to determine crude compatibility. Finally, there are commercial compatibility prediction models that have been developed to determine crude compatibility. Here is a non-inclusive list of such prediction models that can determine crude compatibility. Additional information on these companies' technologies as well as information on products and services previously mentioned can be found in our just published strategic report entitled Novel Strategies of Processing Price-Advantaged Crudes in a Volatile Oil Market. Here is our sponsor's experience. The BHGE crude compatibility model is a proprietary mathematical model that can estimate the ASI of a crude blend based upon the ASI values of the individual crudes and some additional crude characteristic values. The example plots depicted are simple two crude blends. The blue data represents the model calculated ASI value on the y-axis versus the blend percentage on the x-axis, 0 to 100%, of one of the crudes in the blend. ASI measurements of physical blends are also plotted validating the model values. Blends containing as many as 8 different crudes have been modeled and lab test validated in a similar manner. The values used in the crude compatibility model can also identify the theoretically defined incompatibility points for various crude oil blends. These would be blends that potentially should be avoided, or more extreme mitigation efforts required. A crude oil database can be developed to facilitate planning of how a new crude, or a new crude blend, may impact the refiner's operation with respect to asphaltene stability. The model also facilitates ASI quantification of various crudes that do not produce a well-defined flock point. How these no-flock crudes behave in the blend is of strong interest, as many of these crudes induce asphaltene instability. Crude traders, buyers, and refiners must have keen knowledge of the important selection and blending criteria in order to properly prepare, evaluate, and process look-alike crudes. While these look-alike crudes may be an economical choice, many problems may arise when they are not selected properly. Without a doubt, crude compatibility is a paramount criterion, as crude incompatibility can lead to asphaltene instability that cause multiple operating issues. The costs from these problems may outweigh the benefits of using cheaper crudes. The problem of crude incompatibility may be especially prevalent in today's market, where refiners are often incentivized to process new crudes for the first time and to use cheaper grades. Luckily, there are models and commercial options available to predict potential incompatibility and fouling. Therefore, it is up to individual refiners to make the right selections to avoid potential problems in operations. This graphic shows the important selection criteria refiners must consider when buying and blending crudes. Thank you very much for watching our video. Join us next month in December for our next video entitled, A Lot of Problems, Fouling and Corrosion, Part 1 Fouling. Sign up today to receive our quarterly technology newsletter, Worldwide Refinery Processing Review. Since it was launched in 1998, the review has become the most authoritative and comprehensive publication of the latest refining technologies around the world. The review monitors commercial technology developments and competition, plant operation improvements and troubleshooting, and R&D trends for all processing units, from the front end to the back end, in a single source. Each issue covers 2 technology topics with the following sections: Market and Technology Trends and Opportunities, State-of-the-Art Technology, Plant Operations and Practices, Refining R&D Alert, Worldwide Installed Capacity, Recent Construction Activity and Completed Construction Projects, Latest Refining Technology Developments and Licensing. As shown in the table, this year's subscription will cover 8 topics, 2 in each quarter. Apart from an annual subscription of the review, individual quarterly issues and individual technology topics are also available for purchase. For more information, contact us at review@hydrocarbonpublishing.com. Thank you to Baker Hughes for sponsoring this video. Sponsorship opportunities are still available for the rest of the seminar series. Please contact Matt Wonder at mwonder@hydrocarbonpublishing.com to sponsor a future video. Thank you to Dr. Irv, who reviewed and commented on this seminar. Soluble Solutions is the petroleum consulting company of Dr. Irv, who has had over 40 years experience in the petroleum industry. The major offerings of soluble solutions are crude oil compatibility testing and consulting and training in refinery fouling mitigation and resid conversion. Dr. Irv's crude oil compatibility tests and model enable refineries to accurately predict the proportions and order any number of crude oils can be blended without precipitating insoluble asphaltenes that cause catastrophic organic fouling. These tests can also spot self-incompatible crude oils that arrive at the refinery containing insoluble asphaltenes, such as West Texas Intermediate occurring 75% of the time. Here are upcoming crude oil quality events. Your comments are appreciated. Please send your comments to info@opportunitycrudes.com so we can enhance the value of upcoming seminars. Disclaimers.